It's recording.
Hi, I'm Daniel Cooney, and I'm presenting proof 5.1, which is the product rule. And so the premise is that if f and g are differentiable functions, then their product, fg, is also differentiable, and dfg of a will be equal to f of a dg of a plus g of a df of a. So we can create a function, the remainder, r of h, such that f of a plus h, g of a plus h, minus f of a, g of a, minus our guess at the derivative here, f of a, that's dg of a, my mistake, dg of a minus g of a df of a. And we can break this remainder up into three components, or three parts, by calling it, by having an r1 of h, plus r2 of h, plus r3 of h. And what we can do is we can take different parts of the r of h and then as well as adding and subtracting different quantities, which essentially doesn't alter the function because you're adding and subtracting the same thing. So we'll start with r1 of h, which we can start with f of a plus h, g of a plus h. And so we're going to subtract off a quantity that you don't see here, which is minus g of a plus h times f of a. We're now going to subtract another quantity that you don't see in the original remainder, which is g of a plus h times df of a. I'll rewrite that. It's poorly written. df of a. And so we're going to take r2 of h. We're going to first add back this quantity so that essentially we are not altering the function. Then we're going to subtract off this quantity, f of a, g of a. And then we're also going to subtract off another quantity, which is f of a times dg of a. And then we're making a third quantity, which will be adding back g of a plus h times df of a, and then we'll also take this quantity minus g of a times. So essentially what we've done is we've taken this remainder and we've expressed it in terms of the sums r1 plus r2 plus r3, which includes all of these terms as well as terms that were not in there, but we've added them and subtracted them, so essentially we've added 0 in a very creative way. So what we can do now is we want to see what happens when the limit of r of h lim as the magnitude of h, or the length of h, goes to 0, of r of h over h. So what we can do is we can take the limit of the three other pieces and see what happens. So we can go take for r1, of 1 over h times, you'll see in r1 of h that g of a plus h will just entirely come out of the expression. It'll be factored out. So then you're left with, on the inside, f of a plus h minus f of a minus df of a. And what you'll see is if you multiply the h into each part, you'll see that this quantity over h is going to go to 0 because by the definition of differentiability we know that there is a derivative, so this will go to 0. We know that the limit of g of a plus h over h is bounded, And if you take the limit as h goes to 0 of a bounded quantity times a quantity that goes to 0, that limit will also go to 0, so that we know that the limit of R1 of h over h will go to 0. So now we can do, this is essentially the same thing, do it over and over again, which makes it a little tedious. R2 of h over magnitude of h. This time we'll see that the part that factors out is going to be f of a. And then you multiply, and then you'll have g of a plus h minus g of a minus dg of a. And so if you distribute the h's into the two quantities, you'll see that this once again goes to 0, because we know that g is a differentiable function, and this is, if it's differentiable, then we know that this quantity over h will go to 0, and that we know that this is a constant, f of a, so the constant, the limit as h goes to 0 of a constant times something that goes to 0 is going to be also go to 0. So now the third, so we now know that we can move on to the third part of the remainder, R3 of h. And we will take the limit as h goes to 0 of R3 of h over the length of h. We see that df of a will factor out. And then we'll have g, on the other part of the expression, we'll have g of a plus h minus g of a. Once we distribute in the 1 over h, we'll see that this quantity, g of a plus h minus g of a, all over h, the magnitude of h, will go to 0 by continuity. We know that the derivative will be bounded, and we know that as the limit of h goes to 0 of a bounded quantity by a function that goes to 0 as h goes to 0 will ultimately yield a limit, will also go to 0. So far we've shown that the limit as h goes to 0 of R1 of h over length of h, limit as h goes to 0 of R2 of h, over length of h, and limit as h goes to 0, R3 of h over the length of h, or magnitude of h, all three of these will go to 0. So we now know that the limit as the magnitude of h goes to 0 of r of h over magnitude of h goes to 0. And thus, we have shown that f of a dg of a minus g of a, f of a dg of a plus g of a df of a is the derivative of the function f of g.